Welcome to another presentation of mine. Today I'm going to talk about the daily spatiotemporal estimator for downscaling grace gravity models for terrestrial water storage and groundwater storage estimation. Before that, I present my colleagues. Farzam Fatolazadeh is currently my student at University of Sherbrooke, and Khalifa Goita is his main supervisor. I collaborate with these guys regarding these GRACE missions and downscaling, also hydrological modeling. So the idea is that to somehow overcome the shortcomings that the GRACE model has, the GRACE data has, we all know that the GRACE data or GRACE gravity models are available on a monthly basis. If you want to have daily data or higher spatial resolution of GRACE data, then we have to use other sources of information to add those frequencies to the GRACE models. That's the idea of this poster. Here we want to present an estimator which by using that you can put the GRACE gravity models inside the estimator, and also you have to of course add additional information to containing higher frequencies to get the test water storage or groundwater storage. It's very important for decision makers about the water problems, also about the environmental problems. But here we want to provide the better information with a better data so that they can take right decision. So then, as you will observe here, let's zoom the other side of this here. The estimator that we want to present here is a statistical type. But generally, downscaling is done in such a way that the average of the monthly data, the average value of the monthly preserved. For example, if we have monthly GRACE data, we add these frequencies or the higher frequencies in such a way that if we take the average of them, we come to the same mean value, monthly value for the GRACE. That's for downscaling, but we should emphasize that downscaling is not the same with interpolation. Downscaling is to add more higher frequencies. And for adding high frequency data are needed. For downscaling, two methods are available: dynamic method, dynamic method, which you have to use some theories about the water movement and many other things that I'm not going to go to details about, and then a statistical methods which tries to merge different types of data and combine them. One problem that we observe actually in downscaling is this lack of attention to the frequency content of the data. For example, we have seen different studies that they put GRACE data in a system of equation and they will add other data with higher frequencies to the same system and solve them solve this huge system of equation by least squares. Of course, you will add some frequencies by that, but Generally, when we put this, when we add this type of data on top of each other in a least square in a system and solve it by least square, our main assumption is that the data or the differences between the data or the variations of that we see that they are of noise level or random nature. So if you have some data with lack of frequencies, which or they do not have enough frequency, and you add high frequencies data, and you put them in the system of equations solved by least squares or other things, it means that you are assuming that the data has the same frequency content, which is not this. It's not true, because the lack of frequencies you have, or the frequency differences that you consider here, is somehow you consider as a noise or random, which is not true. That was the main reason that we came with this idea, actually, to somehow separate those frequencies, to combine those frequencies, to combine the information based on the frequencies of the data, not to put them in a system of equation and merge them. To do so, we use the spectral combination, which was introduced by Scherberg in 1980. And the idea of Scherberg was to combine satellite gravity models with the terrestrial data and Stokes integral on that time. So the point was that the terrestrial data contains full frequencies, all frequencies, theoretically, but not satellite data. Satellite data are always limited to a specific degree or a specific frequency. So the idea of spectral combination that Scherberg presented at that time was to somehow combine the same contents of the frequencies together, not all frequencies of one data to low frequency data. So not that. Just those parts of data, those frequencies of the, for example, terrestrial data up to degree n, or the specific degree of the gravity model. We use the same thing, we use the same idea here. And here, instead of terrestrial data or gravity data, we have hydrological model. And for the GRACE data, of course, we have the GRACE models. But the idea is this process is not that simple, because for static applications or like geodetermination, so we do not have time limits. They are static. But for GRACE and hydrological, they are time dependent. So the main objective of us is to provide such an estimator so that we use these GRACE models and also hydrological model, and by combining it in an optimal way. And at the end, we will apply it on Canadian prairies. So if I focus on the estimator, let us see. I guess I show the GRACE array. So you see the estimator that we propose here for this. The mathematical developments are presented in the paper and the thesis work of Farson. But what I'm going to explain here is that based on the, let me use the pointers here. Here we have the monthly GRACE model, but this is in a spectral form. Spectra of the GRACE models, monthly models, and this is the error of the models, monthly model, And here we have a Kn. Kn is a coefficient which convert monthly data to daily data. But from where it comes? Actually, if we have the hydrological models spectrum, let me call it TH here, THN, is the hydrological model spectrum divided by the monthly average of the same signal. In that way, this monthly average of this hydrological signal is come here. If the monthly average of this hydrological signal is the same with the monthly average, then we get the monthly hydrological signals, monthly hydrological signal from hydrology. But they are not the same. Therefore, this coefficients, which is actually this ratio of the daily to monthly hydrological data, comes to somehow calibrate and scale the grace monthly models and convert them to the right. But it is not only that. We have an AN coefficient here, which allows this conversion is not solely just to multiply this together, and we have to do some estimation. This AN will be is a coefficient, that spectral coefficient, or actually in such a way that we combine these two models optimally. The idea is that the error of this estimator will be error and the bias will be minimized. So the mathematical developments are actually available in Farzam's thesis or in the paper that he's writing now for the time being. And at the end, we got this IN coefficient. So this KN coefficient contains the frequency contents, the frequency and the signal spectra, and also error spectra of the coefficients which comes from the gravity models and the hydrological models. So let me clean and focus on the other side of the. So we have applied actually this, let me back. We have applied this theory over Canadian prairies for 11 months. But but we do not present all of them here because it's too many maps will appear here. Therefore, we selected three days: the middle of August, middle of September, and October. And you see the values here. These are the daily groundwater storage anomalies that we have computed. So it means that the terrestrial water storage is estimated by the combination of the combination of the hydrological models and also with GRACE models. And this terrestrial water data are used to compute the groundwater storage. How? By subtracting the effect of the other hydrological parameters like soil moisture, snow water equivalent, canopy, and other factors, and then we come to that. Yes, yeah, this data that we have calculated this for 11 months on a daily basis, and but we cannot present all of them here. Here we present some validation. We compare this groundwater storage estimation method, and we estimated the groundwater storage over these Canadian prairies, as you saw in the figure, but compare it with 60 piezometric wells. You see some plots on the left side. Just selected one. Actually, these are not. Was not possible to present all of them. But as you see, The green and smooth line, rather smooth line, are those that we have estimated by the OR estimator, which combines grays and hydrologic models. And the blue one is the in situ groundwater storage anomalies from piezometric, and there you will see a very good correlation between these two. And also the numbers and the statistics are seen on the right side, as here you see. And in this statistic, we will observe that the RMSE, root mean square error of the differences for the 60 was is around 10.60 millimeter up to 47.8 millimeters, and around 15 of them, or 20% of the total total wells are less than 20 millimeters, and 44 or 75% smaller than 30 millimeters. It shows a very good agreement actually with what we have estimated and what the piezometric wells show. However, we should admit that there are also some errors in the piezometric wells that maybe some smoothing is needed, which is not, we should investigate a little bit more. If the variations are of random nature or not any trend, this needs some special analysis over the wells, but we have not done it in this study. And you will observe that about the correlation is between 43% up to 92% for 60 wells. And I do not repeat this, and but you will see that 90 that about 90%, in 40 and 90% is that's a good correlation actually between the estimated and what. So this was so that this method works well and is rather successful. But as I said, there are some things that regarding to isometric wells that can be considered for getting even better improvement, better correlation. But we should first make sure that these piezometric wells and the variations that we observe here are really signals and not noise. So that, okay, thank you very much for your attention and listening to me.